Good morning. We're going to get into another lecture today about the action of gears, and specifically we're going to try to fill in some gaps today about some issues that are not really discussed to me in the fullness that they need to be in the textbook today. And the specific issues that I'm going to mention here that I'm going to get into are the ones of the idea of arc or angle of approach and arc or angle of recess. And so we're going to try to help you get a couple of equations that you can use to get those kinds of parameters that don't automatically show up in the textbook. So that's kind of the main thing we're doing today. As a little bit of background, let's review what it is that makes a good set of gears. Okay? One of the things that it mentions in the textbook is that most gears are designed so that they obey a principle called conjugate action. Conjugate action basically says that as two cams, it really applies to just cams, but as two cams go through their range of motion, the ratio of angular velocities between one of the bodies and the other one maintains a constant value throughout the entire range of motion. This point here is just to basically say gears are elements that have a series of cams that basically are designed to basically interact with one another in the way that I'm showing right here. What that basically means, I can kind of show you an idea of what that means with this picture over here. What you can kind of think of is as these gears come close to each other, you will notice there's a spot where the gear teeth initially come into contact with each other over on this end. And I should give you a little bit of background here that we are assuming with these two gears that the upper gear is being driven with a torque in a counterclockwise direction, and there's also a reaction torque in a counterclockwise direction on the lower gear. Okay? This is important because this tells us where the contact is going to happen between the gear teeth, right? It means that this tooth right here is going to want to push leftward into this tooth right here, while this tooth right here is pushing rightward into this one, right? So we're not really looking at the contact that may be happening over in this pair, because that's not the direction that torque is biased between the two gears, if that makes sense. So anyway, we look at where that contact first gets made between these two gears, and then as we sort of track how that contact will move through this gear's motion, you will notice that there's a constant ratio of angular positioning between the two gears as it moves along. Okay? That is essentially conjugate action that's happening there. Why this is important is you will notice this contact point has not left yet at this point right here. See that? And yet now we've just gotten, just a moment ago, we just got another contact point going up here. In order for this contact point to basically simultaneously apply force at that contact point and at this contact point, they have to have the same speed of their basically progression along this line. They have to have the same angular velocity ratio implied between both elements, or else it won't continue to have contact at that point. So this is one of the reasons why conjugate action is important for these gear mates, is that we want there to be able to be this smooth transition from one tooth to another of how this force is going to be transmitted between one gear and another. Now I'm going to move this a little bit further forward. You'll notice what happens here if we move it along is that that point actually reaches eventually a spot where it comes out of contact, right? It kind of reaches the end of this little line right here, and then at some point it no longer contacts. One of the things that you would like is to make sure that the next tooth that's going to be carrying load has already come into contact before this one leaves, right? Otherwise, you're not going to get smooth transmission of torque from one thing to the other. The other thing that I want to point out to you as this thing moves along is there is this, I'm going to get into this deeper in just a second, but these two blue circles that I'm showing on these two gears are kind of important. These are called the base circles of these two gears, okay? And what these base circles do is they establish the geometry that we need to actually come up with the shape of these teeth, okay? The shape of most gear teeth out there are shaped according to something that is called an involute curve. An involute curve is something, this is actually an example of how an involute curve might be generated. Basically, look at what's happening here. It starts right here, and imagine having a string wrapped around some kind of a rod or something like this, and you tie a pencil to the end of that string, and you start to allow that to trace whatever curve happens as you unwind the string. So the length of that string continuously gets longer because you're unwinding it off of the drum, and that's creating this interesting shape of curve that's happening right here. For us, we don't need it to unwind sort of infinitely. We need it to unwind just a little ways, okay? The reason for this is you can actually see it looking back up at this picture. This line of contact where the contact point happens through the action of this gear is based on a line that extends basically tangent to one pitch circle of one of the gears over to being tangent of the, I said pitch circle, the base circle is what I meant to say. The base circle of one of the gears down to the base circle of the other gear, okay? This is kind of interesting, but basically the action of these gears act as though there is a string wound up on this base circle of one of these gears over here and is unwinding and being wound up onto the gear that's on the other side. All of the action of the gears is basically consistent with that action, as though we could take a string and wind it up around one of these base circles, and then we're winding it from that one onto the other base circle. Okay? And as you look at this, it's kind of hard to kind of bend your mind this way, but taking this gear and allowing it to move, like I was showing just a second ago, actually represents the same kind of action as unwinding a string off of the drum. I don't know if you can kind of see how that happens, but this would be kind of like the string, and as you move this gear, it's like that string has kind of unwound a little bit further off of that base circle, right? This is essentially why the involute curve is a really good shape to be able to transmit torque in this way. It creates a nice straight line. The points of contact, are very well behaved along that line. They satisfy this conjugate action principle, and so we end up with a really nice smooth transfer of torque from one piece to another. Before I get into what we're really trying to do today, I want to just help define some of the terms that I'm going to be using and variables that I'm going to be using to basically represent some of these ideas. So first of all, when two gears mate with each other, they do so in a way that also kind of obeys another principle, and that is that there's this other circle called a pitch circle, and the behavior of the gears is consistent with these gears acting as though there are these two circles that remain tangent to each other, and they transmit movement one relative to the other as though it was two drums that essentially have frictional contact between each other, right? And actually probably in most of your classes where you've talked about gears up till now, that's been the model that you've had in mind, is that you treat it almost like it's just two drums that just have frictional contact relative to each other. The reason that that's valid to do is that gears with these involute shaped teeth that obey this conjugate action, they actually do behave as though that's the action that's happening, right? That's one of the other advantages of having that shape of tooth. So anyway, the diameters of those pitch circles I'm going to call D sub P and D sub G. The little subscripts there I'm going to call the ones that pertain to the smaller of the two gears that are in this mate. I'm going to call that one the pinion, and then the larger of the two I'm going to call a gear. Okay, that's pretty good. It's pretty consistent with what the book does in terms of the terminology of the two members that are involved in one of these types of interactions. But also, throughout my little discussion here, I'm also going to be assuming that it is the pinion that is driving and the gear that is being driven, okay? So that way we sort of have in mind what direction that line of action is going to be oriented. Kind of the angle of that line of action is set by which one is driving and which one is driven, okay? The next thing that I'm going to show you here is the idea of a tooth count. So when I have letter N, that represents the number of teeth on one of these gears, and again the subscripts just refer to both the pinion and the gear. In order for two gears to actually properly mate with one another, they have to have consistent sized teeth, right? Otherwise they won't mate with each other. And one of the ways that we can use to describe the size of a tooth so that two gears can be compatible with one another is with this parameter called diametral pitch. This is actually the one that is used primarily in the US system of gear making. It is based on the number of teeth per inches of diameter, right? So that's when we talk about this equation right here, the diametral pitch, capital P, you take the number of teeth and divide by the number of inches of diameter. It is customary in this system to just give a number, right? So you might say the diametral pitch is 10 or something like that. What you mean by that is 10 teeth per inch of diameter, right? Even though you would drop the unit whenever you're kind of colloquially talking about these measurements, okay? In the SI system, there's, because we always have to be different, right? In the SI system, instead of talking about diametral pitch, they more often talk about something called module. Module is basically how many millimeters is it per tooth, right? So it's really the reciprocal of our diametral pitch that we talk about in the US system, right? And it's actually defined that way here, that the module with lowercase m there is the amount of diameter of the pitch circle divided by the number of teeth, okay? And units in that case will actually just be in things like millimeters, right? Whereas up here, officially the units would be in like 1/inches. All right, I mentioned this a second ago, but you have to have the same diametral pitch between two gears for them to mate properly, or else you'll have different sized teeth and they won't actually go together. Okay, and that's true for modules as well, because that's just flipped the other, it's just the same parameter, but the reciprocal of it. If we want radius values, all we got to do is just take them and divide them by 2. So I'm just kind of mentioning here that when I talk about r sub p or r sub g, I'm just taking half of whatever the diameter was for the pitch circles, right? This is important in multiple ways, but one of the places is important is that sometimes you want to know what the center distance is between the axis of rotation of one of the gears and the axis of rotation of the other gear. That is just going to be the sum of your pitch radii, right? So you just take your pitch radius of your pinion plus your pitch radius of your gear. That gives you your center distance that you need for your gears that you're doing. The other way that you can get that, if you don't want to first find the radius values, is you can just add together the pitch diameters and take that result and divide it by 2. All right, this is mostly just to get y'all kind of comfortable with some of how I'm going to denote some of the parameters that I'm going to use here in just a second. Let's look even deeper. There's a few other things that I think are important for you to be familiar with respect to how gears mate with each other. One of those is that the involute curve that you actually use to generate these teeth, even though it may look like that involute curve would go all the way until it gets somewhere down here in the base, that is not actually how that involute curve happens. The furthest down it can go is down to the base circle, because that's where it began to be generated. But the trough that is cut in these gears is actually deeper than the depth of where that involute curve is going on. Okay, so just kind of be aware of that. What we do is we actually have the extents of where that involute curve goes to at the top end is basically cut off by something that is called an addendum circle, right? It's basically what's this outer diameter out to the limits of the teeth of these gears. And in standard gears, this addendum is set up by basically taking 1 over your diametral pitch P, right? Now, there are some other standards that might be out there for these teeth, but if you have things that are called full depth teeth, this is how they are set up to be. This is kind of the size of that addendum circle, is based on the addendum being added on to the pitch circle. Does that make sense? Okay. When you think about the dedendum, right, a dedendum is basically how far below the pitch circle does this groove that is cut in the gear go. And it isn't surprising maybe that it is usually a little bit bigger than the addendum. Why would this be? This is because you need a little bit of clearance down at the bottom of there. You don't want the tip of the tooth to actually scrub the bottom of the little trough right there. And so you generally want your dedendum to be just a little bit bigger than your addendum so that there's a little bit of space in there, if that makes sense. Okay. There's another parameter that comes into these sometimes called a circular pitch. A circular pitch is the length of the arc along the pitch circle from one tooth to the same point on an adjacent tooth. So on this picture over here, if I identified this point on this gear right here, the distance from that point to the same point on the adjacent tooth over here along this arc, so it's essentially that arc length right there, that is the circular pitch of this gear. So if you're trying to calculate circular pitch, there's some formulas to do this that I list right here. I won't get into them, but you can probably look at them and see where they come from without too much difficulty, if that's a parameter that you want. Why do we care about circular pitch? Well, in order for these teeth to properly mate with each other, we kind of have to have an idea of how far apart each one of the teeth is. And it should kind of make sense to us that the amount of space that you have between kind of one side of the tooth and the other should be about half of the total width right here, so that the tooth from the other gear kind of behaves the same way. So this little point right here says the width of space, that's kind of this area right in here, is nominally about half of the circular pitch. Does that make sense? And then that would be true for the other one as well, and therefore when the two gears mate with each other, you have about the same amount of space for the width of one of the teeth as the amount of space that it needs to go into. Okay, now having said that, if you make these exact, like you actually make them exactly half and exactly half, you could end up with approximately zero backlash, meaning that there's zero amount of space where the two teeth can sort of bounce back and forth between maybe if you reverse your torque bias, right? When you reverse your torque bias, if there's any space in here, there might be a little bit of, you might be able to feel that a little bit in your gear train, because you're shifting from transmitting torque on one face of the teeth over to transmitting torque on the other face of the teeth, right? When these are actually set up, they are generally set up, although not always, but they're generally set up to where they don't actually have zero backlash, right? Your gear will actually run just a little bit more efficiently if you have just a little bit of backlash, because that makes it so that you don't have too many things contacting if they don't have to, right? So typically what you'll see is that they'll have some little amount of backlash, maybe about 4/100ths of the module if you're dealing in the SI system, or 4/100ths of 1 over your diametral pitch if you're dealing in the US system. So anyway, the other thing that I'll just mention about backlash is that that is a parameter that is strongly affected by any variations you might have in center distance, right? If you remember back to when we talked about shafts, we were concerned about things like how much is the shaft deflecting, because it may cause a gear mesh to actually start to come apart from from the two pieces, right? It might actually create more center distance than you thought you had initially, right? If that happens, it actually has a very strong effect on what this backlash parameter is going to be, and that can be undesirable in certain cases. The good news is that because we are using these involute shape of teeth, another big advantage of an involute shape of tooth is that if you do have center distance variation where it pulls apart, let's say, a little bit, those shapes of those involute curves are actually robust against that, and they will actually continue to maintain that conjugate action that we talked about earlier. They actually continue to have that property even if they pull apart from their center distance a little bit. So that's another big advantage of using the involute shape of curve, is that it can actually withstand those kind of variations. It's robust against that. All right, let's get into our main thing we wanted to do today and talk about our base and addendum circle radii. So here is a kind of a more zoomed in version of what I was just talking about. You'll notice that pressure line actually extends from one base circle to the other base circle, and it passes right through this point right here that's called the pitch point. Okay? And so what I want to do is kind of, superimpose on top of here a couple of parameters that might matter to us. One is, we've already talked about the pitch radius right here, and we also talked about how to calculate an addendum. So how do you get what the radius is, or by extension you could also know the diameter if you wanted it, but the radius of the addendum circle here is found literally by just adding whatever your radius was to your pitch circle, adding to that your addendum, right? And that addendum, like we mentioned earlier, has some standards relative to the type of gear teeth that you're talking about. Now let's look at another set of issues here, and that is the relationship between the radius to the pitch circle and the radius to the base circle. Because of the geometry of this line, you can quickly see you can construct a right triangle, right, where basically because this line is tangent to that base circle, it makes a right angle where that tangent condition occurs. That makes this right triangle right here, and it allows us to make a relationship between the radius of the pitch circle and the radius of the base circle based on this parameter that's called the pressure angle of the gear. That is one of the big things that has to be specified if you're going to specify some gears. Two gears need to have the same pressure angle in order for them to actually transmit torque properly. And by the way, there's not actually that many choices practically out there in the world for pressure angle. Generally, you will find ones that are either 14.5 degrees, 20 degrees, or 25 degrees. Those are kind of the three big standards for what a pressure angle might be on practical gears out there in the world. There are some other ones, I believe I've heard of ones that are 30 degrees. The larger this pressure angle is, it makes the teeth actually a little bit stronger, but it also has the tendency to make the torque transmission a little bit less efficient because you end up with a larger amount of normal force per unit of tangential force the larger that angle is. So that's why, that's kind of the trade-off that's happening with pressure angle, is you can make the teeth a little bit stronger by having more pressure angle, but you also might lose a little bit of efficiency because you have more normal force happening between the gears. All right, so this is basically that relationship that I talked about just a second ago of the radius for the base circle relative to the pitch circle. You can just do that based on the cosine of that pressure angle, which is repeated up here. I won't spend too much time talking about that, but you'll notice that that pressure angle has to be that angle that exists in that triangle up there. Okay, so this is a formula that if you want to know the radius of the base circle, you can find that with the radius of the pitch circle using that formula. Okay, so now if we want to calculate these things, we can get them with the addendum circle for the pinion being just this sum, or the base circle of the pinion being this r sub p times the cosine of phi. Similarly for the gear, the larger one, that's how they work. Okay, so I'm just trying to set the basis of this because we're going to need to use some of these parameters here in just a second. This is where it gets really interesting right here. Okay, so we need to think about what's called the line of action, right? When we use the word line of action, we've actually used that term a bunch throughout your schooling in statics and mechanics of materials and stuff. It has just a little bit different connotation to us when we talk about gears, because specifically what we're talking about is a line segment that represents where contact begins to where contact ends along kind of this line where the contact is essentially tracing through this thing. So again, let me start this up and kind of we'll start at a point right where these two gear teeth first establish contact. Where does that happen? It's right at the intersection between where this pressure line is, and we said the pressure line has to be tangent to the two base circles, right? It's right where that line intersects with the addendum circle of the bigger gear. Notice that? Like that's right where that point begins to happen. And then as this action continues forward, you'll notice that that point is progressing from here. It's going to progress and go through. Right here would be the pitch point. right? That's basically the point where the two circles are tangent to each other right there. And then it progresses along and you get your last point of contact that happens where? Right when the addendum circle of the pinion side, right, intersects again with the pressure line. Okay? That is the essential geometry that we need to be able to do what we're about to do, and we actually need those 3 points specifically, right? So what I'm going to do here is I'm going to kind of pick these off and say first point of contact, that matters to us, right? The pitch point location, that matters to us, and then the where it breaks contact, that matters to us as well. And I'm going to need to actually trace or kind of do some constructions of some lines and stuff that have all 3 of these points on the same figure, right? And that makes for a confusing diagram because I'm going to show 3 specific positions of these gear teeth, and I need for you all to understand what's going on with that. So that's why I like to be able to show this. I'm basically talking about the same 2 teeth contacting, but it's at the point where they first contact, moving to the point at the pitch point where they are contacting, and then moving to the end at the end of their contact. Okay? So that's what this figure is doing right here. Okay? Notice here that up here I'm showing the position of the teeth where it first makes contact. Right here I'm showing the position of the teeth right at the pitch point, and right here I'm showing the position of the teeth right where it's about to break contact. All right, so now let's get into this. The first thing I want to do is actually construct a right triangle that connects the center of the driving gear to the pitch point, then along, so that would be this blue line right here, then along the pressure line. This is essentially the same triangle I showed you just a second ago. It goes along the pressure line up to the base circle, and this creates this right triangle. Okay? Now, the big thing that we're trying to go for here, one of them at least, is what is this angle of approach, right? So let's define what we mean by angle of approach. This is what it is. This, by the way, is just, these lengths are easily known for that red thing as well as for this red thing, the blue and the red thing up there. All right, angle of approach is defined as the angle from the point where the pitch circle intersects a gear tooth's profile at the position of the first contact to the pitch point, right? So basically, here's what that means. You go from the pitch point and measure the angle over here. This is the tooth that's about to make contact. I need to measure the angle to where this tooth profile intersects this pitch circle. That is what we mean by the angle of approach, that angle. So this is, I'm showing that line right there. It does not have to hit right at the point of first contact because we also have this profile of the tooth that is actually getting into that geometry there. Okay? Now, if you'll notice that, because that line is also going to the pitch circle, it will have the same radius as R sub P that I listed over here initially, right? All we're doing is, you kind of imagine just rotating that line over here just a little ways until it hits the profile of that tooth. Because that's the same length, and because if I take a line from there again back to the base circle again, it'll make an exactly similar triangle, an exactly congruent triangle really to this initial one, and I can actually sketch what that triangle would look like in dotted lines there. So everyone see that? So it's exactly the same side lengths and everything, exactly the same kind of angle and whatnot inside of that thing. And what you will notice is that because this was the angle of approach between the, this line that goes straight to the pitch point and the one that was shifted off by a little bit, that same angle can actually be seen over here, right? Because all we're doing is taking that whole congruent triangle and just rotating it by the angle that represents the angle of approach. Okay? All right, so far so good? The next thing we're going to do is we can actually determine how much arc length along the base circle was involved in this shift, right? All it takes is just thinking of this angle up here as being an angle in radians. If you take that angle in radians and multiply it by the base circle radius, it gives you that arc length right there. With me so far? Okay. Now, here's where this really kind of gets interesting, is that arc length, imagine that that's essentially the length of string that is being laid on the base circle, right? But imagine that it actually continues on, and this length of string continues to go out, and maybe it starts out here right where this, this point of contact happens at point A. Okay? So think about that. We've got this string that goes along this arc and extends out here to point A. What if I took that string, okay, you're imagining the string, but what if I took that string and started to unwrap it with a piece, like a pencil on the end of it? Let me back that up again. I don't want to talk about that yet. Right? What if I took that and sort of started unwrapping the string? What profile would I sketch? The shape of this tooth, right? And actually, that is the action that happens if I allow these teeth to actually move forward up to the next position that I want to look at, right? So because of that, it turns out that this arc length that happens right here, which you can see, like if I was to basically take that arc length and imagine it being along the dotted line, but now I'm taking it along this line over here, and these two yellow lines have to be the same length, it means that the length of this line from point A to the pitch point has to be the same length as this arc length that I just, talked about up here. Okay? This is probably the most difficult thing to see in all of this, but it's because of that way that this profile is being sketched. You can imagine it being like a string that if you were able to kind of pull this up, it would get you to that point. You have a certain amount of arc length taken up. That'll be the same amount of length that goes from point A to point P. Okay? Now, if we want to compute that length right there, A to P, that's actually not that hard of a length for us to compute. The hard part was knowing why it was that we might need to compute it, right? That's why I did all this stuff here at the beginning. That's why this little length right here is interesting. But computing this length is not actually that hard, but it's going to take us looking at geometry on the other gear, right? So the easiest way to go about getting that length right there is to realize that we know what the radius is to the pitch circle for the driven gear down here, right? And we also know, or it would be relatively easy for us to find, what the radius is from the center to the addendum circle, right? Also, we know what this angle is between this green line and this red line, right? It is just going to be 90 degrees plus the pressure angle, okay? So that's what I say right there. This is now a triangle where I can fairly easily figure out RAG and RG. I'm trying to figure out this length up here, but I also know this angle between the red and the green. Probably the easiest way to deal with this triangle is with, you might guess it, the law of cosines. Okay? So the law of cosines basically says this is kind of like your quote-unquote hypotenuse side over here. You've got your other two sides listed here. 2 times the other two sides multiplied together, multiplied by the angle between those two sides. In this equation, what is it we're actually looking for? And what do we know? We know everything except LAP, right? So we can solve for LAP. That's not necessarily a given that you can solve for it in closed form, but it turns out that we can here. We just need the quadratic formula, right? This turns out to be a quadratic equation in LAP, right? And if you use the quadratic formula, which I'll spare you all of those details, you do that along with a couple of trig identities, it allows you to solve for what LAP is in terms of things that you would know, right? Things you would know would be things like the pressure angle, the radius of the addendum circle of the driven gear, right? And the radius of the pitch circle of the driven gear. Okay, you know those things, then you can calculate the length of AP. Right? Now, length AP is only a portion of the total length of the line of action. Right? Because I found how far is it from the first point of contact to the pitch point. Right? But how hard would it be for me to figure out how far is it from the point where contact breaks to the pitch point? Okay? Not hard. All I have to do is do another one of these analyses like I just did, but basically rotated 180 degrees and applied to the other gears. You basically sort of do it the other direction applied from the perspective of the other gear. What I have shown here shows that length right there. And I want to show you here, I didn't spend the time to like construct all the triangles again, but whenever I first figured all this stuff out, this is the picture that I drew for myself to try to figure all these things out. And you can see there that we have those two triangles that I was messing with up there. Those essentially get repeated down here, right? And ultimately what you do is do a law of cosines on this triangle right here to figure out that length. LBP is what I'm calling it here. Okay? And this is what that equation would end up looking like. Has exactly the same form, but it's going to be based, instead of the radii that you have for the driven gear on the bottom, it's going to be based on the radius values you have from the driving gear up there on top. With me so far? Now, this is basically the line of recess. This is after the pitch point. As it starts to move back away, the two teeth start to move back away from each other as opposed to in towards each other. Okay? So we can use either one of these lengths to figure out other things that we might need to know. Things like, what is the length of this arc? Right? Because LAP is going to be the length of that arc right there. So what if I want to know what the angle of approach is? Okay? I know the arc length and I know the radius, right? An angle in radians is the ratio of arc length to radius. So it's literally just that ratio. Okay? This is just a reminder, when you're doing these, just make sure you use the correct radius values for each one of the L's. Okay? This is, I already mentioned this, that's the length of that line. This is what I was trying to get to. How do we get to these angles of approach and angles of recess? Right? All you got to do is take that little bit of line and, multiply it. It's the same as this arc length right here. Multiply it by divide it by the radius value to the center. That will give you the angle in radians. Okay? Similarly for the other side, if you want to know what the angle of recess is, but for the gear, right? Because if you think about this, moving this whole analysis to the other side, we're now going to be figuring out what this angle is, but measured down here, right? So the angle of recess for the gear can be found with the same type of thing, but with LBP and R, the radius to the base circle of the gear. Okay? So now we know how to figure out what those angles of approach and recess are. At this point, it's tempting for people to think, well, now we need to actually do the other two quadrants as well, right? Here's the problem. Trying to analyze the geometry on the other side of this is actually a little bit more tricky, and there's an easier way to get there. Knowing that this thing obeys conjugate action means that at all points through the action, the amount of movement of one piece relative to the other is going to be based on the gear ratio at all points. So if I know the angle of approach for the pinion, how would I know the angle of approach for the gear? All you got to do is take the angle of approach for the pinion and multiply it by the gear ratio, because that'll give you how much angle the gear had to have gone through as this angle of approach for the pinion happened. Okay? So that's kind of what the next thing is that I'm going to do. Because this obeys conjugate action, all you got to do is take the gear ratio, multiply it by the angle of approach for the pinion, and it gives you the angle of approach for the gear. Okay? Similarly, on the other side, the angle of recess for the pinion can be found by the angle of recess for the gear multiplied by the gear ratio. With me on that? All right, now one of the other things that you might care about is something called an arc of approach or arc of recess. And it's tempting to say, well, didn't we do that just a second ago with the length of that little line over there? And the answer is yes, kind of. It's related to it. But the problem is when we do arc of approach and arc of recess, we want an arc not along the base circle, but along the pitch circle. Okay? So what I would suggest to do that is that now we know the angle of approach and the angle of recess for whichever things that we want. We can figure out what the arc length is of approach and the arc length of recess just by taking the angle of approach, right, multiplying by the radius to the pitch circle as opposed to multiplying by the radius to the base circle. Is that with me so far on that? Okay. And if we want to think about the total arc of action, it's just the arc, the kind of the arc of approach plus the arc of recess. In case anyone's kind of concerned about this, these are arc lengths along the pitch circles is what we're talking about here. Okay? Total arc of action is just the sum of those two. Why do we care about the arc of action? Well, it turns out that one of the things that's important for us to do when we're designing gears is to make sure that we have enough of a parameter called contact ratio. Okay? Contact ratio represents, if these things are, let's say, running at a constant speed, it represents, on average, how many teeth are touching at one time. So through some of your time, there's going to be just a single tooth contact. But from some of your time, you're going to have more than one tooth contacting, or kind of more than one pair of teeth contacting for some of the time. So on average, how many teeth are contacting? That's what the contact ratio represents. Okay? And we can calculate that basically by doing this. We can take the total amount of kind of arc of action, right, and divide it by, what is P here, you think? Circular pitch. Okay? So this basically represents, on average, how many teeth are contacting, right? Because the arc of action is the total amount of arc length that you have for it to contact in, and then P is how much of the arc does one pair of teeth take up. Does that make sense? And that gives you this contact ratio. Some guidelines here. You must make sure, absolutely, that you never have a contact ratio less than 1. Why is that? Because you will have a tooth leaving contact before the next one comes into contact. That's a bad situation, right? So a better guideline is to say it's really a good idea to make sure it's about 1.2, right? That's kind of a minimum guideline to give y'all. And then it's really better for it to be closer to more like 1.5. Okay? But 1.2 is sort of that cutoff that we think of at the lower end of what's sort of acceptable. All right? In the textbook, it gives you an alternate formula to deal with this contact ratio based on what? Well, it's based on the length of the line of action, LAB. We looked at earlier how you could find that length as the sum of the two sort of component lengths of that, and divide it by the circular pitch multiplied by the cosine of the pressure angle. Okay? Basically what's going on there is you are converting from length along the pitch circle arc to length along the base circle arc. LAB is actually a length that is appropriate to compare with base circle lengths, right? And therefore, you take a pitch that goes along the base circle as opposed to along the pitch circle. You can get that by multiplying by the cosine of the pressure angle. That equation is actually another spot in the book that you get the base pitch as opposed to the circular pitch. That's basically what they're doing in this denominator right here. Okay? This is another confusing point for some people, is that when they put this equation in the text, they labeled this P as P sub C. Right? Whereas most of the other places that they have in the text that they label circular pitch, they just call it P. Right? But this P is equivalent to this, what they called P sub C in this equation right here. Okay? They're not always super consistent about how they label things, but Now you know. Okay? And that's basically it. So that should give you what you need to be able to do things like find angle of approach, angle of recess, arc of approach, arc of recess, length of your line of action, and contact ratio. And those are kind of some things that are difficult to get with just the plain equations that are in the text. Okay? Any questions on any of that? All right, fabulous.